Okay, this is a lecture on a full wave rectifier. We went over the half wave rectifier in a previous lecture, and this full wave rectifier is not the only type of full wave rectifier circuit, but it is the most popular one, and it's identified by these four diodes. These four diodes are oriented in the way that you see here for a reason. It's not a haphazard type of connection. In fact, this type of diode connection is referred to as a diode bridge. So that's a key term to know. Okay, so again, this term diode bridge, it refers to these four diodes, how they're oriented in this picture. So what we're going to do is analyze this circuit the same as what we did with the half-wave rectifier, the same approach, where we look at how the current will travel through this circuit for each half cycle of the source. So we'll start with the positive half cycle, and as we discussed previously, and as you learned in your circuit theory, your EE201 in class, the polarity across the AC source during the positive half cycle is that the higher end voltage is on the top of the source and the lower end voltage is on the bottom of the source. So current is going to want to flow from the higher end to the lower end, just like water flows downhill. And as we've learned in this class, current will just flow anode to cathode through a diode, so in the direction of the arrow symbol. So let's just follow the path of current. So you see it's going to leave the top end of this source. Okay, it gets here. It's going to travel through D2 because it goes with the arrow of the symbol, right? It's not going to go against the arrow. Likewise, it's not going to go through D4 because that would be against the arrow. Then it gets to where the load is, the resistive load, travels down like this. Now a key point here is that since the current is traveling down through this load resistor, the higher end voltage across the resistor will be at the top side where the current enters. Okay, and that's a key point, as you'll see here in just a moment. Okay, so the current continues here, comes up like this. Now when it gets to this point, it appears as though the current could go both ways through D1 and D3 because the current would be flowing with the arrow in both cases. However, the current only travels through D3 like this to get back to the lower end of the source. See, it wouldn't make sense for the current to go through D1 because then the current would flow to the same end of the source that it came out of, which, as we know from circuit theory, is not possible. Alright, so this is the path for current for the positive half cycle. And as you can see, D2 and D3 are forward biased. They're allowing current to flow through. And D1 and D4 are reverse biased. They're not allowing current to flow through. So that's what occurs during the positive half cycle of the source. Let's see what happens during the negative half cycle of the source. Okay, so we'll use a different color here because I'm going to be on the same diagram. So during the negative half cycle, the polarity of the voltage reverses. Okay, so now current's going to flow out the bottom end of the source and get back to the top end. Okay, so following the direction of current, see now it goes through D4, and then look, it goes through the load in the same direction, which means the polarity of the voltage at the output for the negative half cycle of the source is going to be the same as what we had during the positive half cycle of the source, and you'll see the consequence of that coming up. Okay, so now current flows like this, and it's going to go through D1 to get back to the other side. And the same argument that it flows through D1 here instead of D3 is, again, to get to the other side of the source, because current flows from one side of the source to the other side of the source. So you see during the negative half cycle, it's D2, or excuse me, it's D1 and D4 that are forward bias, and it's D2 and D3 that are reverse bias. So you see these pair of diodes, D1 and D4 and D2 and D3, they alter states during each of the half cycles of the source. Now what this means as far as V out, since the current travels the same direction through the load resistor for the two different half cycles of the source, is that the peak voltage, both the positive peak and the negative peak are going to be on both sides, or the same side we're going to get the same polarity voltage at V out. So effectively what happens, because the current is traveling through the load in the same direction for both half cycles of the source, effectively what happens is that the negative half cycles of the source get flipped up at the output. So we just get a stream of half cycles here, positive half cycles at the output. Now compare that to the half wave rectifier. See, this is the full wave here. Okay, and in a previous video we saw that V out for a half wave rectifier is that effectively the negative half cycle of the source gets cut off at the output. Okay, but you see here with the full wave rectifier you essentially have twice the amount of peaks as you did in the half wave case. And we discussed in a previous lecture that the DC output, the average V out of a half wave rectifier, is the peak voltage divided by pi. Well, with the full wave rectifier, it's just that you have the double number of half cycles. So now if you were to do the same analysis as we did with the half wave rectifier, you would see for the full wave rectifier that DC value of V out would just be 2A over pi. Okay, so you see for everything being the same, you get twice the amount of DC voltage at the output with the full wave compared to the half wave case. And then, as we discussed also earlier, if you put a capacitor, across the output, if we stick a capacitor here across the output, well, that capacitor is going to smooth out these humps. Okay, it's going to smooth out this voltage through the charging and discharging of the capacitor. And now you increase the area under those curves and you increase your DC output amount, just like in the full wave case. Right? In the full wave case it was the same. Okay, that your DC V out is always increased by putting that capacitor across the output. Okay, well this finishes applications of diodes, and we're going to start into looking at the analysis of non-ideal diodes in the next lecture.